Hi, Liz. How are you doing?
Hi, I'm doing great. How are you? Nice to see you again.
I'm. It's really good to see you again as well. Are you joining us from Colombia again?
Yes, from Colombia. And in case people are wondering, this is not a green screen on the back. It's actually my house, and I have a beautiful view and yeah, in the nature.
So jealous. I am properly so jealous right now. It is dark and grey where I am in just south of Manchester in the UK. So it is so lovely to see it. So nice for you there. So Liz,
Yeah.
how have things been going? I hear you've just started a new job.
Yeah, I started a new job like a couple of weeks ago, and it's different, and I'm excited. It's a completely different environment and platform and everything. Before I used to work at Node.js as head of developer relations, and now I'm head developer advocate of FuseBit, which is a integrations platform for developers. And yeah, it's been very challenging, but also very exciting.
Oh, well, good luck with your new role because it sounds amazing. I'm
Thank
going to
you.
hand over to you now, Liz. And Liz is going to be talking to us about maximizing Node.js performance.
Yeah. Hello, everyone. I'm Liz Parody, as you already heard, and today I'm talking about maximizing Node.js performance. LizParody23 is my Twitter handle in case you have any questions or comments. And since it's almost Halloween, I have the spookiest slides of all. So let's begin. There's nothing more terrifying than a slow application. We all hate that. Performance matters, especially when creating software. A 2-second delay in load time in a web page or application results in abandonment rates up to 87%. 67% of customers cite slow loading times as the main reason they will abandon an online purchase. And also, browsers might crawl your site slower if you have a very slow site. It's all related on how our brain works and how our society is structured. Instant gratification is making us perfectly impatient. We want everything instantly now. A lot of people might lose motivation and interest if they're forced to wait. Not only that, attention span became shorter, finding hard to stay focused on one thing for extended period. Fast results helps with attention retention. This is why it's essential to keep the performance of your application healthy. Performance monitoring should be part of your development process to detect possible problems before they're visible in production, not only when issues arise. Technology, applications, and the internet plays a significant role in this fast and furious speed hunt. They have conditioned people to get immediate rewards, and as a result, people got used to it. We all got used to it, and waiting became harder. This talk is divided into 3 main parts for improving performance in Node.js. First, we will be talking about CPU and some tools to improve Node.js performance, such as exposing the VA inspector via the Chrome DevTools protocols, time measuring CPU, performance timing API, and scaling CPU. Then we will be talking about memory, memory structure, memory profile, garbage collection utilization, and finally, we will explore network and cache and load tests. It's pretty easy to write slow Node.js applications. It's very common to wait for a page to be delivered on an API to respond, or to create several parallel requests that take ages to be answered. To get the best out of Node.js performance, you need to focus on resources. Because if your app gets slow, it's because you run out of some resources. And to fix this, you need to monitor the resources and understand what's causing the issue. There are 3 primary resources that we have to hand to fix and improve Node.js performance: the processor, monitoring, and network. The first 2, CPU and the memory, are the most problematic. And even though network is not so problematic, it's essential to mention it. Now let's talk about our third resource, the CPU, the processing unit. If you want to see how easy it is to consume most of your CPU, let's look at the following code. In this code, the while loop runs indefinitely and blocks the process if there's any delay of 10 seconds. If you run this code in a web server, it blocks. No other request will be processed, which is a very bad idea. If we check the activity monitor here, we can see that the CPU is consuming 98%, almost 100% of the CPU. And here we have a little school screaming in there. So this is how you block a process, meaning high CPU consumption. In our server context, that means that if I have two browsers and there is a delay of 10 seconds for every request, the request will take 20 seconds and multiply this for hundreds of thousands and the server just dies. Or the client gets server unavailable or timeout error. So here we have two main issues. First, find out if you have a problem. And second, find out how to solve the problem. Sometimes you don't know where the problem is, and even worse, you don't know how to find it. Luckily, Node.js already provides us with several helpful tools that assist us in monitoring resource utilization. And the first one that we're going to talk today is expose the VA inspector via the Chrome DevTools protocol. If you develop in the front end, you will be familiar with Chrome DevTools. A few years ago, Chrome DevTools was integrated directly into VA, expanding its capabilities to include Node.js applications. Using this flag that you can see here, node inspect break, and the file name, you will be able to inspect your Node.js applications in Chrome DevTools. As we can see here, the message is printing the console is debugger is listening to WS followed by a WebSocket. So this is the WebSocket. And WebSocket makes it possible to open a two-way interactive communication session between the user browser and a server. We can also see a message that redirects the user to the Node.js documentation so we understand what is happening here. This is the Node.js documentation here. Then, if we go to the URL Chrome inspect, or even better, about inspect here, you will see something like this. That will let us do a link. It locates the remote protocol on the underlying VA engine, and you can connect your Chrome DevTools with a Node.js to debug the Node.js process. So you don't have to get new tools, just your browser tools, no CSS or HTML, just plain JavaScript. Once you click on that link, the DevTools node link, you can see a pop-up window for debugging your Node.js session like this. DevTools is now connected to Node.js, providing you access to all the Chrome DevTools features you're familiar with. The second tool we have in hand is time measuring CPU. CPU load can be measured using various external tools, such as HTTP, built-in tools, or external tools. Now the question is, how to find if you have a problem? One option is to open DevTools and click on the profiling tool that gives you a CPU profile. This will tell you how much time it takes to run a specific function, process, or resource. Even better, you can use NSolid to take CPU profiles. CPU profiling allows you to understand where opportunity exists to improve Node.js processes, speed, and load capacity. To take a CPU profile, you just go on the process detail and page and click Me CPU Profile, as you can see here in this image. Oops. Then you select a profile window between 5 and 60 seconds, so you can see here. The thread you want to see, 0 is the main thread, the rest of them are worker threads, and the desired visualization style to run a profile. Take into account that NSolid is the only tool available that lets you monitor and take CPU profiles and heap snapshots of your worker threads. Then we click on Start Profile. This is a flame graph of NSolid. As we can see in our example code, there's clearly an issue highlighted here in red that points to the problem. This is another visualization of the same function. In this case, we're using a sum burst visualization. So now we will have solved the first issue of finding out your performance problem with a CPU profile. Let's go to the second issue, which is actually solving the problem. The CPU profile will tell you exactly what line of code or which function or which file is causing the issue on consuming your CPU. So you can go to the source code, find that function or statement, and fix it. As we can see here, the problem is the if statement that is taking 9,000 milliseconds, almost 10,000 milliseconds. This has to be fixed. A function that takes more than a few milliseconds, it will give you performance issues for sure. Measuring CPU is a good indication of the locations of your performance problems. Before you mess around with your code, find where the problem is. Maybe you're in the wrong source code and you need to prioritize where your problem is located. At the end, it's all about the execution time. The execution time is the time it takes the certain blocks of our application to execute from start to finish. The easiest way to track this is to use console time here, as we can see here. Console time is handy when you don't have access to Chrome DevTools or any other tool to take CPU profiles. So this is telling me that this code to start to finish is taking 9,000 milliseconds. The third way of checking CPU performance is Performance Timing API. In Node 8.5 introduced a new module for time measuring, the Perfux module. This API allows developers to set various markers that makes calculation the runtime of an application easier. With these APIs, you can measure the time it takes to in individual dependencies to load, how long your app takes to initially start, and even how long individual web service API can take. For example, the following code will measure the performance of the top search engine, Google, Yahoo, Bing, DuckDuckGo, using performance hooks. As we can see here, we have performance observer, we have some marks here, performance mark, and then we have a performance observer with the entry types that would console log the duration of each entry. In this case, we can see that Google is the fastest one with 165 milliseconds, and Yahoo is the slow one with almost 1 second, which is super slow. Let's look for another example, just for measuring the execution time for this super simple Hello World app using performance and performance observer. So we have performance here, and we just console log Hello World. We get the list of entries, and here we call this function. We will see that this simple Hello World app takes 12 milliseconds, which is super fast. While the performance observer is informative, there are some trade-offs. It requires instrumentation of the code manually, impacting readability. In the case of performance observer, there is a significant overhead cost to the observing, which is not good. The significant advantage is that you can turn it on and off. So you can have these measures in your production application, and if you experience some performance problems, you can turn it on, take the measures, and then turn it off. Then you will have a snapshot of your real applications, and you can dig in to your performance problem. This is a very cool feature, useful for critical production applications, especially when you have a relatively long-running processes and you want to find out if you have a performance problems. For most cases, like 90%, these features should be turned off, so it doesn't influence the overall performance. When you turn it on, the system gets a little bit slower. You shouldn't turn it on every case because of the performance costs. Take into account that most of the performance tools have a cost, also called overhead. The traditional APMs have an overhead between 5 and 20%. In comparison, NSolid, the top performance tool for Node.js, has an overhead less than 0.5%. You don't have to turn it off because NSolid won't affect your performance as other tools and features. As you can see here, NSolid is faster. And finally, scaling. Scaling Node.js so we don't have CPU performance issues. We want applications that can scale, and there's several possibilities to scale a lot, either locally or in some cloud infrastructure. Single-threaded, non-blocking performance in Node.js works great for a single process, but eventually, one process in one CPU is not going to be enough to handle the increasing workload of your application. No matter how robust your server might be, a single thread can only support a limited load. The fact that Node.js runs in a single thread does not mean that we can't take advantage of multiple processes and, of course, multiple machines as well. Using multiple processes is the best way to scale a Node.js application. Node.js is designed for building distributed applications with many nodes. This is why it's called Node. Scalability is baked into the platform and is not something you start thinking about later in the lifetime of your application. For this, we can think about 3 ways to scale: child processes, worker threads, and containers. So, child processes. A key strategy to work around scalability and the single-thread nature of Node.js is to launch a child process or a process created by another process when faced with a long-running task. When a new process is launched, the operating system can employ multi-processing techniques to ensure that the main Node.js process and the other child processes run concurrently or at the same time. We can use child process module, as we can see here, number 1, to create new processes. And those child processes can easily communicate with each other with a messaging system. Take into account to not span more child processes than have cores in your system, because every child processes come with a certain amount of overhead. Also, child processes come with potential problems such as shared resources. Let's imagine that you have a server on a virtual machine with multiple cores, and a single process can only load one core up until 100%. Using the child process feature, you can use nearly every core of your system, usually between 2 and 4 cores available. However, you should at least have one core available for your system itself, because you have 4 cores, and when you not use processes in all of them, your system gets slow automatically. You can create child processes using spawn, exec, file, and fork. Let's use, for example, fork. The fork function allows you a two-way communication between the parent and a child processes. For example, this is my parent file, and this is the JS file, my child JS file. In this parent file, we fork child.js, which will execute the file with the node command. And when we listen for the message event will be emitted whenever the child uses process send, which we can see here. And this is doing it every second. So this message will print every second, counter 0, 1, 2, every second. And yeah, I just stopped it to not make it like infinite. It's recommended to control your child process. Give them a maximum limit, fork child processes, and reuse them. You don't have to stop the processes and don't open the gates for a possible attack. The next one is workers. The primary purpose of a worker thread is to improve the performance of a CPU-intensive operations, not I/O operations. For I/O operations, we can use child processes. That's the main difference between worker threads and child processes. You should not use workers for I/O-intensive operation because Node.js handles async I/O operations internally most efficiently. So this is an example of how you can use worker threads to send a message. We send a message via post message, as we can see here, and then we register it with the on method and use a callback for the message event. Finally, we have NSolid that you can use to get the metrics from the CPU of your Node.js applications and know when you need to scale it up. You can create CPU profile, and this is how a CPU profile looks like in NSolid. CPU profiling allows you to understand where opportunity exists to improve your Node.js processes and speed and load capacity. Now we're going to containers. So this is a real-world example where you can start using the Node.js application in a Docker container distributed in your preferred infrastructure. This is a straightforward example for an Express application and a Docker file. When it takes a current image from a Node.js 12 and then exposes to the port application we listen to, in this case, 8080, and npm start with just start the application, you can run 50,000 containers and you don't have to deal with scalability problems. The container will just handle it. Oops, I thought I turned my phone off. Yes, sorry about that. Okay, so continue with this. We have node behind a node balancer. This image represents a good, here, node behind a node balancer. This image represents a good infrastructure. You can have the containers behind a load balancing, and infrastructure deals with scaling. Load balancing refers to efficiently distributing incoming network traffic across a group of backend servers, also known as a server farm and a server pool. Modern high-traffic websites must serve hundreds of thousands, if not millions, of recurrent requests from users or clients and return the correct text, images, videos of applications data. Okay. Yes. In order to cost-effectively scale to meet these high volumes, modern computing best practice generally requires adding more servers. A load balancer acts like at the traffic cop, sitting in front of your servers and routing client requests across all the servers capable of fulfilling those requests in a manner that maximizes the speed and capacity utilization and ensures that no other server is overworked, which could degrade the performance. If a single server goes down, the load balancer redirects the traffic to the remaining online servers. When a new server is added to the server group, the load balancer automatically starts and sends requests to it. Now let's look at a memory, our second resource. It's easy to consume large amounts of memory when creating memory leaks and affecting our application. Node.js allocates memory to keep all objects in the current scope in memory. By default, the memory is limited to 512 megabytes, which should be enough. However, this limit can be increased with the max all space flag, as we can see here. And you can increase the memory to 2 to 4 gigabytes. So looking at memory structure, this is how memory management works under the hood. There are two spaces in our memory, the short-living objects and one where the long-term memory lives. Take into account that most objects only have a short life cycle. The memory management system is the reason why you should reuse objects as much as possible. If you reuse objects, this will go to the green square, and the garbage collector is much more efficient if you reuse the stuff because it doesn't have to kick out objects from your memory. So if you can reuse an object structure, also known as classes, and you just change the property, your application will get optimized by the JavaScript engine. The most critical concept in this section is reuse structure. By doing this, your application gets optimized and fast. If you always throw away objects and create new ones, your application gets slower because the garbage collector is being overused. Let's say, for example, how to consume large amount of memory, which is a very lousy practice. This code generates a callback function that doesn't allow the garbage collector to free space. Then we use set interval to consume even more space. This could be hidden somewhere in your application, which is a very bad idea. Even user can consume all of your memory. You can limit the creation of a number of objects because in any other case, your system will crash on memory exceptions, or your system is using the hard drive as memory, which will get slow. When we create code that consumes large amount of memory, we have some options to find the problem. First, we have process memory usage. In Node.js, giving up the heap size and the heap use, as we can see here. Process memory usage, heap total, and heap use. The result is measured in bytes, but it would be best if you didn't do this in production because it keeps filling your logs, which is not good. This is mainly for bug finding purposes. If we run crop DevTools, we can go to the memory section and we'll be able to see this here. This is the heap size and the trend of the heap size usage. We just press the garbage collection button and it frees up memory. If we run the application with the previous code example and visit the memory endpoint, the memory grows and grows. If we press the garbage collection button, the function leaves execution context and the memory gets freed up again. This is the first indication where the memory consumption is going. If you end up here, you're probably having memory issues. This is the memory snapshot for an application in Chrome DevTools. And if you have to dig into this one, we find many objects are consuming your memory and finding out where your memory goes, and it's not simple and easy because there is a lot of noise. And finding out which specific object is consuming your memory can be challenging. JavaScript objects tend to be very small and need to locate very small items in a lot of noise. In this image, we can see the constructor here, the shallow size, and the retained size. It's important to know what this metrics means. Distance is the distance of the object of the root object. Hold on, that sounded weird. Is the distance of the object to the root of the object. The root of the object means that if your object is deleted, it has no parent object. Then the shallow size is the size of the memory that is held by the JavaScript object itself. And the retained size is the size that gets freed up if the object is deleted. If you have an object with a very small distance, it can free up more space because it has more children, and the children get deleted recursively if the parent is deleted. We can also use NSolid to do this and compare snapshots. Now let's talk about memory profile. If a snapshot is a photograph in memory, the profile is a video. The video helps you to find your memory problem because it points you to your own code. It's advisable to go first with a profile and then to the snapshot. The garbage collector, well, currently it's not possible to trigger the VA garbage collector manually. However, you can trigger it from your DevTools for debugging purposes. You can press the trash button and the garbage collection will run, freeing out memory. This is how it will look like. We just click to trash. And now we're going to the final part of this talk and also the last resource, which is network. If you go to the Network tab on Chrome DevTools and request your application endpoints or resources, you will be able to see if you have problems. In general, use the network panel when you need to make sure that resources are being downloaded or uploaded as expected. The most common use case for network panel are making sure that resources are actually being uploaded or downloaded at all, and inspecting the properties of individual resources such as HTTP headers, content sites, and so on. If you're looking for ways to improve page load performance, don't start with the network panel. That is why this is the last part of this talk. There are many types of load performance issues that aren't related to network activity. Well, I'm going to speed up because my time is almost gone, but we also have Morgan, which can help us with memory, with network. Caching, there is external caching and internal caching, and caching is great for network. There's load test, which will help us, is basically destroying your application on purpose, finding out how much load your application can take. Yeah. And there are several tools for this, like Apache Bench, will tell us how much load our application can take, and also gbetter, which is also super useful for like load tests. And finally, some tips and tricks on Node.js performance. First one is test with live data. Anonymize whenever you do a performance test. No fake data because it's not trustworthy. And don't send emails with your load tests to your customers. Then run regular load tests before every release in a regular intervals to know if a new feature decreases the performance of your application. Define performance metric and observe them. A request has to take a maximum few seconds to be completed. Whenever you hit the metric, you have to do something, work with those metrics. Communicate with your ops team and keep an eye on your production metrics because they know infrastructure best. Do performance tuning wherever needed. It's cool to do performance optimization, but do them on purpose. The micro optimization costs a lot of money. Just don't do micro optimizations. And they don't get you like anywhere. And finally, use cache and optimize resources. And that's it. So thank you very much. And I would super appreciate if you can follow FuseBit on Twitter. Here, this is Twitter. I'm trying to grow the social media presence, so they will keep allowing me to do this type of talks. So thank you very much.
Thank you so much, Liz, and thank you for your excellent talk. And what a fantastic theme for October as well. So it was very appreciated by a few people on the channel too. And I did also notice that you changed your terminal to match your theme as well. So that was amazing.
Yeah,
I very much enjoyed your traffic cob as a load balancer analogy too. That is a really good way of thinking about how load balancers work. So thank you for making that very clear. I'm just going to see if we've got any questions. There's been quite a debate about the amount of memory within the Node versions. So that there was some discussion around the 521 megabyte in the latest Node versions, and it might actually be 1.4 gig now, but there is an anecdote of somebody who increased it to, and this is amazing, 32 gig and things still works. So that seems like a huge amount.
It is. Well, I appreciate you invited me here. Is there any questions? Or
I don't have any more questions for you at the minute, and I think we are going to have to move on to the next speaker. So thank you ever so much. But if anybody has any questions, they can contact you on Twitter, yeah?
yeah, thank you. Bye.
Bye.